Let's talk about similar figures. We're at the point in geometry where we need to move from congruent figures to similar figures to study our last transformation. Our topic is similar figures. Our lesson is to define what makes shapes similar. We will use this definition to determine if shapes are similar or not. By the end of the lesson, you should be able to use ratios to demonstrate whether shapes are similar. You studied ratios last year as a 7th grader. Understanding similarity is necessary when we study the transformation of dilation later this week. Similar figures are figures that have the same shape, but not necessarily the same size. These two trapezoids are similar, but they're not congruent because they're not the same size. Similar figures are similar because the length of their corresponding sides have the same ratio. Corresponding means in the same location, remember? I'm still using that vocabulary. So right here, we're looking at this short side of the rectangle, which is 2 meters. And right here, we're looking at this long side of the rectangle, which is 4 meters. So our ratio is 2 to 4 or 1 to 2. Basically, this is saying that this is 2 times as big as this. Well, let's see if it works down here for our long sides. We have a 3-meter length and a 6-meter length, so the ratio is 3 to 6, which equals a 1 to 2 ratio. And again, this is the same ratio. This is 2 times as big as this side here. Our ratios are the same, so these two figures are similar because they have the same ratio of 1 to 2. And this ratio is also known as a scale factor. This shape right here is twice the size of this shape right here. All right, similar or not similar? Here are some triangles, and these are similar. Pentagons, these guys are similar. Same shape, but just not the same size. Over here, not similar, we have two triangles, yes, but and they're different sizes, yes, but this is a right triangle and this is an isosceles. And here are 2 pentagons, yes, but you can see that these have totally different dimensions. All right, let's look at some examples. One of the ways we can tell if figures are similar, we can go ahead and make a table to show their similarity. So here's our small triangle. Here's our big triangle, in case you didn't figure that out for yourself. So let's go ahead and look at the bases of these. So the base of the small triangle is 15, and I'm going to just put up here in centimeters so we don't have to write centimeters after every piece. So the base is 15 over here, and over under the big triangle it's 20 centimeters. And let's go ahead and look at this side of the triangle. On the small triangle it's 12. On the big triangle it's 16. And then our final side, on this side it is 6, and on this side it is 8. So now we need to test our ratio theory. These have to have the same ratios each side. So for the first one we have is 15 to 20. This can be reduced. 15 and 20 both have 5 as a common denominator, so we can, or common factor, so we can divide both by 5. 15 divided by 5 is 3. 20 divided by 5 is 5. So we have a ratio of 3 to 5. Excuse me, 3 to 4. Hello. 3 to 4. It's late. All right, 12 to 16. Greatest common factor of 12 and 16? You got it. It's 4. It is 4. So 12 divided by 4 is 3. 16 divided by 4 is 4. There's our ratio again, 3 to 4. Our final side is 6 to 8. 6 and 8 have a common denominator or common factor, which is 2. So 6 divided by 2 is 3. 8 divided by 2 is 4. And there we go. These figures are similar because they each have the same ratio. Their corresponding sides have the same ratio. All right, let's look at these triangles here. Are they similar? Well, let's take corresponding sides. We'll look at this side right here. we have a 6 to 10 ratio. 6 and 10 have a common factor of 2. 6 divided by 2 is 3. 10 divided by 2 is 5. Let's check the other side. 15 and 25. So our ratio is 15 to 25. 15 and 25, their greatest common factor is 5. So 15 divided by 5 is 3. 25 divided by 5 is 5. And again, we have this common ratio. Now, here's the secret if you're dealing with triangles. If two of the corresponding sides have the same ratio, then the third has the same ratio. So yes, these are indeed similar. What about here? Pause the video now if you think you want to try this one on your own. Otherwise, write it down for a second example. We have the short side of our rectangle, and it is a 4 to 8 ratio. Greatest common factor of 4 and 8 is 4. So we divide both by 4. 4 divided by 4 is 1. 8 divided by 4 is 2. So we have a 1 to 2 ratio. The long sides of the rectangle, we have 6 centimeters and 12 centimeters. Greatest common factor is 6. 6 divided by 6 is 1. 12 divided by 6 is 2. So our ratios are the same, and these rectangles are similar. How about here? Once again, if you want to pause the video so that you can try this on your own and then unpause when you're ready to check, feel free. So let's go ahead and see our ratio here. We have 18 to 12. Greatest common factor is 6. 18 divided by 6 is 3. 12 divided by 6 is 2. So this is a ratio of 3 to 2. Then we have 24 and 16. And the greatest common factor there is 8. Very nice. So 24 divided by 8 is 3. 16 divided by 8 is 2. So we have this ratio of 3 to 2. Now, we can use this ratio to figure out what this length of the triangle is because we know this length. So we know that 21 over whatever is right there is going to give us a ratio of 3 to 2. Right? Okay. So we can we can go backwards. 3 times what gives us 21? 3 times 7. So we can go backwards from here and multiply this by 7 and find out that 14 is the length of our missing side. All right, practice problems. Go ahead and pause the video while you determine if these shapes are similar or why not. Unpause when you're ready to check your work. Okay, here we have 16 to 8. Greatest common factor is 8. So we have a 2 to 1 ratio. Down here, 6 and 3. Greatest common factor is 3. So we also have a 2 to 1 ratio. These are similar. And they are similar because they have the same ratio. What about these triangles right here? Again, pause the video while you work this out for yourself. Oops. Okay, we have an 80 to 10 side. Greatest common factor is 10. So 8 divided by 10 is 8. 10 divided by 10 is 1. And down here we have 88 to 11. Greatest common factor is 11. 88 divided by 11 is 8. 11 divided by 11 is 1. So we have the same ratio. Remember, you're not looking for the same greatest common factor. We're looking for the greatest common factor to see if there is the same ratio, which there is. So yes, these two triangles are similar because their ratios are the same. All right, something different. I want you to use your ratio to figure out these. I'm going to tell you that these are similar. So because you know they are similar, you need to try to figure out what this missing side is. If you want to try it on your own, go ahead and pause the video and unpause when you're ready. So we know that this side is 45 and the corresponding side is 9 miles. Greatest common factor of 45 and 9? Right, that would be 9. So we're dividing both numerator and denominator, or ratios, by 9. 45 divided by 9 is 5. 9 divided by 9 is 1. So just like in that problem before, we know our ratio is 5 to 1. So the 25 goes up here, and then that will allow us to determine what our missing side length is right here. So how did we get from 5 to 25? Right, we multiplied by 5, so the ratio has to be the same down here, so 1 times 5, and we know the length of our missing side is 5 miles. Try this one on your own as well. We have two quadrilaterals, not trapezoids, and we have corresponding sides, this long side right here. So one of the sides is 56 feet. The corresponding side is 8 feet. Greatest common factor of 56 and 8 is 8. 56 divided by 8 is 7. 8 divided by 8 is 1. So we know our ratio is 7 to 1, and we know that 35 goes here, and then that'll help us figure out what our missing side is. So 7 times what gave us 35? 7 times 5. So down here, 1 times 5, and again, our value for x, our missing side, is 5. But this one's 5 feet. The other one was 5 miles. Please make sure that you note which parts of the lesson confuse you or that you have questions over so we can go over this in class discussion. See you in class.